Good morning, all. Just starting the live stream now. Not much going on. We've got some signals from Chandrayaan-3 here, so we'll just monitor those for a while and see what comes up in the live chat. Test. Okay. Hopefully my audio is half decent. So, a couple minutes ago I was just showing you guys some of the steps that I take to reduce the Doppler data. Let me bring some of those screens back up. So this plot here is the plot of all the radio signal that I've copied since the satellite rose. And you can see the white highlighted line is the data that we've copied, matched to the trajectory and the TLE that I came up with yesterday. So we're right on track. Nothing has changed. You can see here the frequency is rising. Somebody asked earlier why the tone was going down. It was probably because I was on the opposite sideband on the audio when I moved the carrier around a bit. But everything's fine. We have very low residuals. Everything is matching up nicely. So let's go back and have a little bit of a look at some of the analysis steps that I did there. So you're wondering what I was doing. Got lots of terminal windows open here, so I just need to find the one that is actually relevant. There we go. Okay, so there's 3 pieces of software that I used. This is all from Case Bass's SatTools RF, STRF as it's known. So the first command that I issued was the command RFFFT. So basically what it does is it takes the raw IQ data that's being stored on the hard drive from this radio signal. And somebody had asked earlier what all this means. This is the central carrier. These are the data sidebands. And these are just some carriers' residual RF energy from the mixing of all of this together. And this forms one of the various frequencies that Chandrayaan-3 is using. This particular one at 2203.2 megahertz I've found it to be the most stable. It doesn't seem to, the operators of the spacecraft don't seem to change its frequency much, so I'm using it as our Doppler study case here. The other channels, one of them right now I'm also monitoring this morning, and we'll have a quick look at it. It is also sending telemetry. It's at 2284.6 megahertz, and I'm using SatDump right now, and I have the decoder set up for it. It's got about a 7 dB signal-to-noise ratio, and it's steadily improving. The spacecraft is sending turbo-coded data. Unfortunately, for whatever reason, the ISRO hasn't optimized the turbo system to really give you really weak signal decoding capability. So we'll have to wait until it's around 10 dB or so before the CRC check will pass, and then data will start recording to the hard drive. So right now we're at about 49,000 kilometer distance to Chandrayaan-3, and I would expect somewhere sub 40,000 in the 30,000 range. This will lock up nicely. So that'll be another 3 dB or so. So meanwhile, back to what I was talking about with respect to the Doppler analysis. We'll get that screen back up. Like I said, I've got lots of windows off screen here. So FFT, it takes the IQ data that we're recording now that we understand what the signal is, and it extracts that and converts it into binary files of the FFT data. So basically it makes a frequency and time binary file. So the next step is we plot the data. So here I'll do that command right now so we can see it. It reads the binary files that were created during the FFT step. And each one of these is a 1-minute file. So it stores 1 minute of data. As you can see, there's lots of them. So it takes a second because there's a lot of data here that it's got to process. So this window comes up. So this is a plot, and there you can see this is the prediction for Chandrayaan-3, which is NORAD number is 57320, and you can see the trail, the actual signal plotted there, and you can see the data sidebands up here. It's not the most graphically friendly program, but it does do the job. Here I'll increase the contrast a little bit so you can see the similarities between it and what's on the waterfall at the moment. And also point out a few other things. Okay, so you see the noise level here, the background is quite high early on. That's because my antenna is aimed into trees. So this is when Chandrayaan-3 rose above my trees and I started to get a clear line of sight. So there's a command called M that basically looks for peaks in the signal in the waterfall display and plots it. So this is now output a file onto my hard drive that will allow me to extract the data and study it in yet another program. We'll notice this little number here, Z max, so we don't have to adjust the background next time. So I'm just going to copy that, and then we'll quit out of this program, and we'll just add the Z max into that so it's in the queue. I'm just going to abort that now. Now we'll go to the RF fit, and you notice later I just used this out file. So this allows me to go in and remove all this noise that I don't want to study because it's not related to the signal at all. And you can see Case has put in some handy editing tools that allow you to just grab a hold of and get rid of the stuff you don't want to study, the noise. So now we're left with a nice Doppler curve, but we have nothing to compare it to. So we'll save it, and I'll just call it test data for this purposes here. See, it saved 20,983 points of data. We're going to quit out of this, and then we'll go back and we'll take our test data, load it up, but this time we're going to compare it to the orbital elements that I have, that I've created. You can see here that there's a track in the sky. There's the TLE from yesterday that I shared with everybody. I'm going to select the data. Now I'm going to fit it. Now, it's not correcting for any orbital elements. It's just raw fitting the data to the expected trajectory of Chandrayaan-3 right now, or when the data happened. Now I'm going to highlight an area outside of that curve. So now this is in the future. This is in the past when I didn't hear the signal. And there's the complete Doppler curve. As we can see from the RMS fit, very low, like 8.4 Hertz. If we zoom in, we should see the white line overlap the red line very precisely. And as you zoom in, it does. Now, you might notice as we zoom right in that there's a little bit of difference. Well, we can try to correct for that. So I'm going to adjust for ascending node and mean anomaly. So that allows me to minorly adjust the plane of the orbit and also the timing of the spacecraft. And I'm also going to throw in a bit of adjustment for mean motion, which is the orbital period of the spacecraft. So now I'm going to fit all of those. It's going to take a little while. It's going to crunch some numbers. And you can see the fit has improved. The line matches better. So the more data that we've gathered today, has helped us update this orbital element. And that makes sense because we're now approaching perigee. You can see the curve is starting to become a little bit more dramatic and interesting. This hook up here, this Doppler reversal, is the gold standard when you're doing high Earth orbit orbital analysis. This is essentially the effect that perigee has on a high Earth orbit signal. It comes in, there's a Doppler shift curve. You see the rate change from going up. It drops down, and it drops very abruptly. And this is due to the perigee. And we can use that to very precisely determine the orbit from Doppler data. So very handy. So over the course, you can see here, this is the predicted Doppler through perigee, and this is when I'll lose observation, right there. So when it goes gray, that's when I won't be able to see it anymore. And if you look at the sky plot, this is where the spacecraft is now, where the cursor is. It's going to carry on over here a little bit, and then it's going to follow this trajectory over the next couple of hours. And we should have pretty good signals from it all the way down until it sets on my local horizon, even with some tree interference down in here. So I hope that's a bit helpful, and I hope my audio came through. It says I'm sending audio, so let me know with your questions. So, yeah, if you have any questions, just fire it into the chat, and I'll try my best to answer them. I can provide some demonstrations if you like, or whatever. So as far as the radio configuration here, I'm using two SDRs today, two new-end Blade RF2s. It's all coupled into the same antenna. I have a splitter that I'm using. There was a link I'd shared earlier with you guys that shows you some details on that. Maybe what I'll do is I'll bring the radio the actual schematic diagram up that I have, and we can share that with you. Just give me a few minutes. Okay, so this is the schematic diagram of the S-band receive system. So out on the roof there's a 1.8 meter dish that has a feed system connected to it. It's an orthogonal feed system, so I can use left-hand or right-hand circular polarization. Presently, I'm using right-hand circular polarization because that's the sense that Chandrayaan-3 is sending. From there is a low-noise amplifier. At the present time, I don't have this bandpass filter in line. It's switched out for other experiments. And I have a very low RF noise environment here, so I rarely need this unless I'm pointed at some areas of the geobelt when I get interference from some commercial spacecraft. A line amplifier feeds down to the Radio Shack, and inside the shack I have a Wilkinson splitter, or a hybrid, here that splits to two SDRs, and presently I'm not using the EDIS B200 SDR. I'm using two Nuand Blade RF2s that are feeding into a couple of different computers. The whole system is GPS referenced, so the SDRs their clocks are referenced to the GPS frequency standard, and that is critical for Doppler analysis. That's what makes it so accurate. So that's the S-band receive system in kind of a nutshell. Get you the feed for it. So the feed system is this. It's basically a waveguide, circular waveguide feed with two orthogonal probes and also a choke. The general design was developed by a radio amateur here in Canada, VE4MA, and I've scaled it for my use on S-band. Here's some details of the actual probe and waveguide assembly. Pretty simple stuff. It's actually a piece of 4-inch irrigation pipe that I used to build it, and it works even on its own quite well. This is a geostationary satellite just with the open waveguide. And here I've cobbled on a horn antenna to do some other tests with the initial thing when I was setting it up, and I could see the GOES satellite TT&C beacon carriers in geostationary orbit with it. The choke assembly, I had to build a ring to support it. Tried to keep it as light as possible and used really light aluminum flashing and assembled it that way. There's the complete test assembly on the ground, and it only weighs less than a kilogram, the entire assembly, which is what I was aiming for, keeping it really light. Presently I'm using an RF hybrid for creating left and right hand circular polarization. Not exactly the most efficient method. It eats up a little bit of my noise temperature, but for most of what I'm doing it's pretty acceptable. Here is the mount for the dish. This is on the test stand in the backyard, so I can access the antenna and work on it. You can see how the mount works for it, and it does a pretty good job of keeping the antenna aimed. Here's some details of the assembly under test on the test stand in the backyard. This is me just setting up. This is an old hybrid that I actually use in the shack now for creating circular polarization for a test setup here. Most likely I was doing some tests here, sun noise. More details of how the system is set up. So these plots here give you an idea of, this is in order to test your S-band antenna or any microwave antenna for that matter, you can use the sun as a reference source. This is during my calibration process with the system. I did let the sun drift through the field of view of the antenna, and it allowed me to actually calibrate how sensitive the antenna system was and compare it to the known solar flux level. They record the solar flux out at the DRAO in Penticton. They have a special antenna there to collect that data, and they post it online. And what you can do is you make concurrent observations with your system, and then you can calibrate your flux level that you're hearing from the sun to their level that they're hearing at the same time, and calibrate your antenna so you know exactly how sensitive it is. So I did this in horizontal and vertical polarization, and further testing. When you get to S-band, hearing natural radio sources from deep space is incredibly difficult with small antennas. The flux levels drop right off, and you know it's quite the challenge, especially with a small 1.8 meter antenna. However, I was able to hear Cygnus A through a drift scan, revealing how sensitive my antenna system is, and you can see the calibrated GT ratio there. So this is an image of Dishy McDishface up on the roof, and that's what's tracking Chandrayaan-3 right now. And here's another view of it during setup. Show you a bit more about the setup on the roof. There's the mount, and you can kind of see the trees and stuff around me. This part of the mount is kind of critical. This allows me to level the antenna system and also rotate it in azimuth for calibration. So this assembly allows me to calibrate the whole system so the antenna can be aimed and tracked accurately. And this is just the bandpass filter and line amplifier box up on the roof. So you can see here some earlier results with the KPLO at the moon and NASA's wind out at the Earth Sun L1 point with the system as I was testing it up. So that gives you a summary of what the receive system is here. I did provide this link to this moment on Twitter, so if you're interested you can check it out. And I also keep it up on my GitHub site. Much of this information is available here in a request that we sent in to participate in the Artemis Doppler demonstration project with NASA. So you can have a look there too. I'll throw this link on the chat for you guys. There you go. So, okay, so let's get back to looking at some Doppler curves. So you can see here the signal is definitely increasing. We're getting let's have a check and see what's going on with decoding. We're not quite there yet for CRC, but I think we'll probably see that starting to occur within the next few minutes, and then we'll start recording some telemetry data from the spacecraft. This particular channel, I believe, is associated with the propulsion module, as is the 2203.2 megahertz channel. So I would expect we'll start to see CRC passes starting to occur shortly. We're at about 46,000 kilometers distance, and this is a 2 kilobit per second link, and it's pretty much the same as what we have here on the GQRX setup. Okay, just reading through some of the questions. There's quite a few came through here since I started yapping. Exam Pirates asks, what's the difference in orbit achieved and orbit desired in the last burn? It was very close, to the point where I would be commenting about noise, not really anything intelligible in signal and difference. So I think the ISRO accomplished their aims. There wasn't much of a difference at all between what was claimed and what was observed. So I think the entire part of the mission so far in Earth orbit has gone, I think, entirely according to plan. And if there had been minor deviations, which is very normal in these kind of operations, they would have just corrected it during the next burn. So I doubt that there was anything significant. Certainly nothing observed in the data that I collected that suggested any sort of major shortcomings in the trajectory during any of the burns thus far in the mission. Another question is, can I show you guys the approximate place where the TLI burn will occur during the Doppler curve? Yeah, let's do that. So first of all, let's get the Doppler curve up. So here's our test data. Let's fit that, and then we'll zoom out so we can see what's going on. So as I mentioned earlier, the red line tells me when I should be able to see the satellite. It's above my horizon. The white line is the actual data that we've collected so far and reduced. So this is all in the future. So this highlighted area is the perigee. TLI, translunar injection, is going to occur somewhere here. So I'm not sure whether I'll be able to see it. The burn will probably be many minutes long. I'm not quite sure, right? And maybe some of the viewers here have some more data that they've seen from ISRO or heard through the media in India. Typically these kind of burns, they're not instantaneous. They take many tens of seconds to even minutes to perform. And so we may see some. Unfortunately, as the satellite descends, its radio signal will have a few challenges. First of all, the antenna on the spacecraft is somewhat directional, and as it approaches perigee, just visualize this. The spacecraft is up there right now quite high, and it's got an antenna aimed at Earth, and most of that antenna beam is covering almost all of the Earth that it's seeing, because it's relatively far away. As it gets closer to the Earth, that beam of that antenna is only going to encompass a smaller and smaller area of the Earth, and then the spacecraft is hurtling so fast towards the Earth that it's not really keeping that orientation of that antenna precisely aimed at any particular spot per se. And it's not really a fault of the design of the spacecraft, because as it approaches perigee, generally the spacecraft is not trying to communicate with the Earth anymore, and it's just running an automated program to do whatever it's supposed to do, fire its rocket or do nothing, as it, many of perigees that it's passed through so far. So the radio signal will get wobbly, it'll fade up and down, it won't be strong, and particularly on my horizon, I'll be looking into a forest, so we might not hear much from it. And if we do, it will probably just be the central carrier, this big, strong peak tone that you're hearing right now, but it'll be rather weak. So I'm not 100% sure we'll hear anything from the TLI. If we do, we might see it in the Doppler as a deviation from this. So you'll see this, the data will deviate from this line. That's what would tell us that we're seeing the rocket firing and the spacecraft accelerating, and its line of sight velocity with respect to what was predicted will be different, and the data that we're getting will deviate from the prediction that we've got right now. So that's basically what we would see, or if we had a really good clear view of the translunar injection at perigee. But we really don't. So let me bring up this plot. So this is a representation of where the spacecraft is right now. So I'm going to make a couple of changes here to kind of accelerate time. Give me 1 second. I just need to find the appropriate window to make the changes in. So I'm going to change the step interval to 10 minutes, 600 seconds. So as you can see, we're accelerating in time, and now I'm going to rotate the view so we can see where perigee is going to happen. And I'm going to zoom in. So now you get a kind of a clearer picture of what's going to happen at perigee. We're getting close to it. We're going to accelerate another 10 minutes. So this dot right here is where perigee is predicted to occur. Now I'm going to change the time interval to 60 seconds. And you can see the ground track, this circle right here. And this is where I live and our radio station is. We're not going to see that. But that doesn't mean we're not going to perhaps see something occur from the translunar injection, because I lose signal at approximately, it's hard to read that, 1831 UTC, and it arrives at perigee at 1844. So there is a possibility that the burn could be quite long and we might see something. I really doubt it, but you never know. Let's be positive. So I'm going to reset this back so we can see the current position of the spacecraft. So there we go. Okay, so that's that question, and let's move on to the next question. The rotor I'm using. Okay, so let me dig out some info on that, and I'll be right back. Okay, so here's some details on the Pelco mount. It is a Pelco. It was surplus. It's a a PT1250P/P, so it has like the potentiometer sensors inside. It's 120 volt AC unit, and here is it arriving after purchasing it from eBay. I actually have two of these. There was a company in Seattle that was selling these pretty much in new condition, surplus, a few years back, and I acquired a couple of them. Within North America, it was a pretty reasonable deal. The shipping was good, and so that's the unit. This is what it looks like inside. Very robust. The unit's capable of 100-pound plus payload. I didn't modify much. Mostly some of the limit switching and stuff like that was where the major modifications. The connector, you can get these from DigiKey. They often don't come with cables and connectors, so you need to deal with that. The wiring diagram for it, quite simple, just AC synchronous motors. You can very easily calibrate the potentiometer sensors for azimuth and elevation. Here's the DigiKey part numbers. I do have all this information up on Twitter. I can share a link to the part numbers if you're interested. So some earlier experiments with another pan tilt mount. Not much to report there. So that's the mount I use. There's a moment that I have here that I will share the link to, so it's got some more details in it, and that should give you some good info about that. Somebody asked what that signal was moving left to right. I'm not 100% sure what it was, but guess what? We can find out. With our handy STRF, we need to reduce the data again. So, first step, oops, I kind of jumped the gun here. So we need to delete some data. Star.bin. So I'm just going to delete all the data we just reduced a few minutes ago. And just make sure what I'm doing here is the right thing to do. Okay, good. Okay, so now we're going to go back into the Wayback Machine here. And I'm going to reduce all of this, and this is to answer the question, what was that signal that passed through that an eagle-eared observer heard? This is a very handy feature of STRF, is it allows you to not only study things you're interested in, but also find out stuff that you didn't know existed until it passed through the signal and wondering what it was. So we'll have a look there in a second. Let's get rid of this. And we're reducing the data. You can see here it's chugging away. What it's doing right now is it's converting the IQ data to bin data or FFT data in 1 minute chunks. Each one of these bin files is 1 minute of data. Yeah, while we're waiting for STRS to chug through it, there's another question on what's going on with the CRC. We're still hovering around 9-10 dB. It should click in once I get a reliable. Still don't have CRC lock. And we should see that in time though. It's really odd. to use turbo coding and have apparently the sequence that they're using for the correlator is really short, so it doesn't allow it to build up signal to noise ratio using the coding. Okay, so let's go back to here. Perfect timing. Okay, so our next step is to plot the data, have a look at it. And we're trying to answer the question, what was the mysterious signal that passed over Chandrayaan-3's signal? I'm going to switch back to that. And wait for the plot to come up. Okay, so there we have the plot, and somewhere in here we had this mysterious signal, and there it is. Now what I'm going to try to do is extract a bit of the curve. Don't know how well this is going to work, but there's good enough data there. Okay, so now we'll exit out of here, and we're going to go somewhere in here. We have that. There's our Doppler curve. Need to clean it up a bit. There's a bit of noise in here. Don't need that. That looks okay. Save that as test. Now, onID.data. Okay, so we've got that. So now what we want to do is compare that. So I need to, first of all, I'm going to update my orbital elements. So I've got the latest orbital elements from the US Air Force or Space Force, and that should be good. And then we're going to fit. So what we do now is take our test unidentified file, and we want so now I have one large file here that contains all the TLEs. So now I have that. We'll load that up. We'll select this, and we will find the unidentified satellite. So what I'm telling it to do is search the entire catalog and compare the Doppler for every satellite that's in the NORAD catalog to this Doppler curve for my location at the time that it was heard. So it's got one hit. It's within the error limit. This error code is just some data that's in the system that generated probably an error. So it identifies as object 54035. So what is that? So let's find out. Throw up another terminal window. TLE info, another little useful program that Case has come up with. So 54035, and it's a Chinese mission, HJ2E. So there you go. Your question is answered. So now, because it's not in my, I've now logged that. So it's now in my frequencies, and we can go back to here, and we're going to plot that data again. And something magical will happen. So every time we monitor this frequency area and that satellite passes over, I will be reminded as to what it is. So I'll give it a minute or so while it chugs through all this data. I'm doing 10-second integrations here. So normally with STRF, for a lot of common uses, you would use maybe, 10 Hz bin blocks. Normally you'd use 100 just to kind of minimize the wear and tear on your computer. But I'm using it for this mission. I'm using that. So you can see here our friendly Chinese satellite. You can see that green line now perfectly identifies where it should be. Just like it's identifying where Chandrayaan-3 is. You can see here, it's got its own green line. So, did we see this satellite earlier? Weakly, we did. The addition 10 is not aimed anywhere at it, so it's going to be a very weak signal. But you can see we heard it on the previous pass too. And there's another satellite that was heard in the past, but we're not hearing now. So there you go. That's one of the useful applications of STRF and being able to track and identify objects that pass through your field of view. So, yet another mystery solved. Okay, moving on. Okay, somebody's asking a question here. I'm not sure. Will it appear as a Doppler curve on satellite? I'm not sure what the question is in context to, maybe what we just discussed. As far as filtering out debris and stuff like that, well, you could, but you never know if the debris is misidentified as an object. So I generally don't. I just leave the whole file there. We've seen rocket boosters being used as, objects with small radio transmitters and stuff like that on them, and so it is possible that debris could be misidentified as an actual emitting object. So I generally just leave it. Yeah, there's someone made a comment, is it a Chinese and Indian mission? It just totally coincidental. The dish is not even aimed at the Chinese object, and it just happened to be strong enough to be detected. Even though it wasn't very strong, it's very common to see many objects using similar radio frequencies. So no big deal. No, it was a real satellite. I see your question there, clarification, thank you. Yeah, it was a real satellite, and again, no relation to Chandrayaan-3, and they're probably not even remotely close to each other. This object is in low Earth orbit, probably anywhere from 500 to 800 kilometers. I haven't run the numbers. We could do that, but it's nowhere related at all to Chandrayaan-3. It just happened to be the radio signal just happened to be at the same frequency as Chandrayaan-3 this morning. So get rid of that, and we don't need this up anymore, and we don't need that. So let's check in on our decoding correlator is building up a bit more. Still not a super strong, well, it's a pretty strong signal. It just, unfortunately, the decoding system isn't the optimized. So we'll just keep monitoring that. We're at about 41,000 kilometers now, and I'm going to take a break for a few minutes and just let you guys enjoy some more Doppler tones, because I know it's very soothing. So here you go, and I'll bring the pitch down. And there you go. Okay, so on the 2203.2 channel, we have finally got CRC pass and we're decoding telemetry. Exciting stuff. So what does this telemetry look like? Well, let's have a look at it. Give me a minute or so to get up the bit viewer and we will do some sleuthing with the telemetry. Okay, so we want to open the telemetry file. And it's the current one right here. We've got a few kilobits of telemetry. We've got to deframe it. And there's the telemetry frame. You can see there's some counters, stuff like that. So let's zoom into it. And so if we go and look at the binary part of it, this first 32 bits is not actually sent by the satellite. It's part of the CADU file that SatDump creates. But this part here is the spacecraft ID. And this correlates to the propulsion module, and you can see it just repeats. And then over here you can see timers and counters. If you switch to hex, there's 13C. That is the spacecraft ID. That's its call sign. It uniquely identifies the propulsion module of Chandrayaan-3. So if you go back and look at this is the bit raster view of the data, and you can peruse it. We haven't dug into it too deeply. I'm sure somebody like Daniel Estevez or others will dig into it at some point. There's probably not a lot going on with the propulsion module other than routine telemetry, as I believe it only has one relatively simple science experiment on it. So I'm not sure what we'll see from it apart from just routine telemetry, which this kind of appears to be. So if we clear that off and we reload the file, you see we've got 24 kilobytes now. Properly frame it, you can start to see the structure of the data forming up here. And you can zoom into it a little bit. You can see counters and other structure in the data. We'll come back and have a look at this in a bit. So right now we're getting telemetry decode there, which is good, and I'm going to start a few more instances of SatDump. Which will allow us to loiter on other channels, because this will be the last chance we really have of copying telemetry from Chandrayaan-3 with smaller amateur antennas. So let's get as much data in the can as we can for posterity. Unless, of course, ISRO changes the turbo coding and makes it more compatible with weak signal work. Okay, I'm just going to stop the decoding on this channel, and let's go have a look at some of the other channels. So This has wider data on it. As you can see, the signal isn't quite as strong, so I doubt it will decode for us. It's, I believe, 8 kilobit per second. Let's see what we get. Yeah, it's not quite there. Something odd going on here. Okay. It did not like something about that. Okay, let's get sat dump going again here. Go back into processing. And let's see if we can get... Getting decent correlation, but still no CRC checks. So I'll have to come back and look at this in a bit. So let's go check out one of the other channels. This is one I haven't been monitoring much. It's got wider data on it as well. Certainly not strong enough to decode. Not yet anyways. So the spacecraft is approximately 35,000 kilometers distant. We're in altitude. Distance-wise, it's 35,000 kilometers. Altitude, it's about 33,000 kilometers. So we'll take a look at the last channel that we had been monitoring for a while. 84.56. And we should be able to get something out of this guy now. I would hope. Still no CRC pass. Okay, so we'll go back to the original channel and we'll carry on with our decoding of telemetry there for a while. And start that process. There we go. So once it gets above a certain signal-noise ratio, it just locks and it becomes 100%, which is really cool about Turbo. Like I said, had they used a slightly different setup for it, it would decode very, very minimally, like what we're seeing on Stereo A, like signals that are barely above the Shannon limit are being decoded. But anyways, we'll let that run for a while. Keep an ear on activity on the primary Doppler channel that we're interested in. And we'll lower that pitch so it's not so grating on everybody. You can see a lot more signal dynamics coming into view as the spacecraft descends. The signal will get stronger and stronger, and soon we'll start to see some fading caused by the pattern of the antenna not quite aligned with the Earth anymore. We'll start to see some nulls in there as well. A couple of questions I see on. Okay, so yeah, somebody's asking about a TLE, even when it's close to Earth. The problem is the TLE still needs to model going out far away from Earth, and once you get to a certain mean motion to describe the orbit, the TLE won't accurately model it anymore. So you can do a couple of different things if you still want to use TLEs. You can generate TLEs that represent the arc of the orbit for a very limited period of time and issue a whole pile of TLEs that are only valid for a certain period of time. That's possible, but the better method is to simply generate a state vector and an ephemeris table that from that state vector, and use a different reference frame on a different model. So you could use GMAT, which is what I'll be using, and I'll just simply create a new Earth orbit for the Chandrayaan-3 as it goes out towards the moon. And the nice thing about that is GMAT also models lunar gravity. So as the spacecraft approaches the moon and falls under its influence, the orbital model will accurately reflect that. So TLEs I'll discontinue use after this, and the spacecraft should be optically visible at the moon. In previous missions, we've had other amateurs image objects that we've been tracking at lunar distances. I've worked with people that have imaged Quaco at the Earth-Moon L2 point, and other Chandrayaan-5, etc., are all under constant observation by amateur class instruments optically at the moon. So yeah, it's just a matter of getting a decent state vector and keeping track of it that way. Okay, I'm just got a phone call coming in, so I gotta deal with that. Okay, so we've got some good data coming down on the 8 kilobit per second channel. I believe this is part of the lander system, at least based on spacecraft IDs. So we're getting some data, telemetry from this. This also seems to correlate to activity on the Deep Space Network. So let's throw that up so you can see Chandrayaan-3 is in comms with DSS-26 at Goldstone in California. And you can see the range update. We're looking at about 30,000 kilometers range. And it's uplinking on X-band, which is interesting. And there's the downlink. Note that their kilobits per second is incorrect. Presently, the satellite is using 2 and 8 kilobit per second, and they kept this pretty consistent throughout the mission. So whatever data they're using to share on their website is not entirely correct. But we can see here that we lost our CRC check there, but we did get some good data for a few minutes. And I imagine we'll get it again. Let's go have a look at what we captured there. It's a bit faster data than the 2 kilobit per second stuff. Uses the same frame size, but sends a bit more at a time. And the spacecraft is presently in lock. So let's have a look here. So this is the spacecraft ID. It's 244 in hex. Right there. So that's the spacecraft ID, and you can see the counters and everything. There's some other bits before and after that determine some stuff in the CCSDS standard. So, and somebody asked earlier what these were. These are like autocorrelation, looks for patterns, repeating patterns in the data, and that can be used to determine the frame lengths. You can see here, as I zoom out, you see all kinds of them that repeat. The first one correlates to the actual frame length of the telemetry data packet. So that's the bit view of it. So we're just on the edge of decoding the 8 kilobit per second channel. So we'll leave it there for a while and get some more data. The spacecraft is presently in lock and communicating with the Deep Space Network. The couple hours before it arrives at perigee and will perform the Translunar injection burn. So this would be its last real time to communicate for the next hour or so with the Deep Space Network before its orbit brings it very close to the Earth and outside of the slew range of the deep space antennas, where I would presume Chandrayaan-3 will go on autopilot and ignite its rocket at perigee to boost it towards the moon and release itself from the Earth's field of influence. So I'm just going through the 8 kilobit per second telemetry data, and it doesn't appear to be anything overly interesting in the sense there's no ASCII text or Easter eggs in here. But we've got about a quarter of a megabyte of data downloaded so far. There's the bit stream of it. Give you a sense of what's in there. Presently, the spacecraft is in lock with DSS 26 in Goldstone, California, as you can see here on the DSN Now website. And the spacecraft is approximately 27,000 kilometers distant and rapidly approaching the Earth for perigee and the translunar injection burn, which will occur in a little under 2 hours, during which time the spacecraft will fire its engine from the propulsion module and loft itself towards the moon and end the sequence of phasing burns and orbits that it was doing around the Earth to gain momentum so that it could get to this point of finally doing a translunar injection. Okay, just looking, got a question here. When will I do an update on the translunar injection? Well, there's not much to update on other than everything seems to be fine with the spacecraft. Nice steady signal. It's in lock with the Deep Space Network, Deep Space Station DSS 26 in Goldstone, California, as you can see on the plot that I have right up now. Nice steady signals. We're getting the telemetry decode on the 8 kilobit per second downlink from the spacecraft. We just reviewed some of the telemetry a few minutes ago. Here's a summary of it here. You can see we're starting to get an appreciable amount of data. This was about a quarter of a megabyte. Now we're almost at half a megabyte of data downloaded from the satellite. And as you can see here, there's the bit frame of it. So we're doing rather well now that we've got lock. And meanwhile, on the 2 kilobit per second channel, which I'm using for doppler, for a couple of reasons, it's not affected by ground locking, so it gives us a nice steady doppler signal to do our trajectory analysis, which helped us develop the two-line element, or TLE, for tracking while the spacecraft has remained in Earth's orbit, and will bring us down to perigee in approximately 2 hours, where the translunar injection burn will occur. This is not exactly riveting television, but it does keep you up to date as to what's going on in real time with the spacecraft. You're actually seeing live radio emissions from Chandrayaan-3, and here is the location of the spacecraft above the Earth. And over here you will see in the coming hours, as the perigee, as the Earth rotates into position and the spacecraft arrives at perigee, it will fire its rocket engine from the propulsion module and conduct the translunar injection burn. So I think now we've got a bit of telemetry recorded from the 8 kilobit per second channel. I'm going to go and have a look at one of the other channels that I have yet to have success in getting decode from. Maybe in a few minutes I'll do that. Maybe half an hour or so, and the signals will really have built up, so we don't have to disturb the telemetry gather that we're doing here. So we have a long, consistent group of data to maybe study later. Yeah, see some comments here. We should. Some of you may have noticed that the change in Doppler rate has increased over the last hour or so. This is entirely normal as the spacecraft descends towards perigee. Its relative motion compared to the ground station here is increasing. And that's really what determines the rate of Doppler frequency change, is that velocity. So we could do a update on the Doppler situation and do a comparison and see how that's working out with our orbital model. So let's do that. As I demonstrated earlier, we will use STRF for this. And I've got most of the commands already in the buffer here. So first of all, let's get rid of our legacy data. And then let's update the data by running our current FFT. So this will take a few minutes to process all the data since the recording began some 10 hours ago when Chandrayaan-3 rose here above my eastern horizon. Unfortunately, the forest to my east blocked the signal for a few hours before I actually acquired signal, but that really doesn't affect the overall analysis process much. So we're converting the raw IQ data recorded by the SDRs to binary FFT data that we can study. Basically, FFT data is just frequencies and times saved in a binary file format that allows us to just plot the actual signals over time and then extract the Doppler data from that. So each one of these bins is 1 minute of data. And each day has 1,440 minutes in it. So as you can see, we're a considerable portion of the day of data already converted to FFT format. I'm recording in 1 second by 10 hertz bin increments, so we can extract fairly accurate Doppler data to produce two-line elements. Later in the mission, I will still use the same data recording and extraction process, but start using GMAT to do modeling after the translunar injection, so we can account for lunar gravity and also the fact that two-line elements are not designed for deep space type trajectories. So now we'll plot the data. And this is actually going to read all the bin files that we just created, the fast Fourier transform files, and plot them over time and frequency in the ranges that I've provided that will provide us with a raw Doppler curve. The plot will also, because I've already got the system pre-programmed to know where Chandrayaan-3's Doppler curve should be, based on the trajectory analysis we've done to date, the plot software will display that and we can compare it against it as it's running in time. Takes a few seconds. It's a lot of data that it's processing right now. And there we go. So I'm going to cycle here and turn off the overlay. So these green lines with these numbers, these indicate trajectories of spacecraft that are known to use this frequency. You can see 57320. This is Chandrayaan-3. And you can see the trajectory or the Doppler curve of Chandrayaan-3 closely matches the prediction. A little bit of frequency offset I see. What we'll do now is we will extract the Doppler data. You can see here the algorithm in the software is looking for peaks in the signals and has extracted the Doppler data. Just to make my job a little easier, I'm just going to zoom in on this little bit of it. As you'll see in the next step, we're going to leave the plot program and we're going to go into RFFit, which allows us to compare, edit the data. I'll remove the noise here. That's the first step of the analysis. And I'm just removing all of these noisy bits that are not part of the Doppler signal that we want to study. So there's our Doppler curve for Chandrayaan-3 so far today. Now we're going to save that as a temporary file. And then we'll quit out of there. And we will open it up with where did that go? There it is. This is our orbital element from yesterday. So now we're going to fit that against our trajectory model. And as you can see, what we started to discuss was the rapid change of frequency has started to really peak upwards as we approach the perigee of Chandrayaan-3's final orbit of the Earth before it begins translunar injection in approximately an hour and a half. So you can see here, here's the Doppler update. We're steeply rising in frequency, and then we will do a Doppler reversal and begin the plunge towards perigee. Well, it's ongoing. So from here, the data, we can have a look at what to expect around perigee from the Doppler. So the red line indicates where the spacecraft will be visible to us before it's set based on our orbital prediction here. The white line is data that we've already copied, and we can see that we still have a bit of time to go before perigee happens. This rapid descending tone, or descending part of the curve, that is the part of the orbit where Chandrayaan-3 will be passing through perigee. Approximately here where I'm highlighting, this is where the translunar injection will occur. So I will probably not see the effects of the propulsion module firing its engine because the spacecraft will have either set or have set behind trees locally here by that point. However, there is a chance we could observe something, but I wouldn't count on it. If we did, we would see a deviation in the Doppler curve from the predicted line, predicted path. The translunar injection will occur over the Atlantic Ocean, just north of Brazil, and it will be rather low in altitude, approximately 230 kilometers above the Earth. So it will not be observable by most of the Earth at that point. I guess it would be in range of the ESA ground station that's located there. So it may communicate with that, but I'm not 100% sure whether ESA is providing support. Whoops. So that's the status as it sits right now. Everything seems to be fine. No obvious signs of issues with Chandrayaan-3. We're getting good data decode on the 8 kilobit per second channel. The signal noise ratio has built up considerably in the last few minutes, which is expected. And we will continue to copy telemetry from excuse me, Chandrayaan-3 until we lose signal. Presently, the spacecraft is approximately 23,000 kilometers distance from my ground station and approximately 21,000 kilometers in altitude above the Earth immediately below it. So it is rapidly descending. The apogee of this present orbit is approximately 127,000 kilometers, and the perigee is approximately 230 kilometers. Okay, another update. Chandrayaan-3 continues to remain in lock with DSS-26, the Deep Space Network. Spacecraft is approximately 22,000 kilometers in range, altitude approximately 20,000 kilometers above the Earth subpoint immediately below it. So what does being in lock with the Deep Space Network mean? It simply means that it's in communication and likely ranging with the ground station. So it's exchanging data, maybe accepting commands and preparing for the TLI, and also engaging in ranging activities where the Deep Space Network will provide precise data to ISRO about the range to the spacecraft to help clarify its trajectory in very, very precise terms. So that's what's going on right now. Nothing unusual. This is normal spacecraft activity. Meanwhile, we're monitoring a couple of different channels at the moment. Chandrayaan-3 is presently transmitting on 4 different frequencies on S-band, 22.03 megahertz, 2241 megahertz, 2268 megahertz, and 2284 megahertz. We're presently monitoring 2203.2 megahertz. That channel has very good stability for Doppler analysis. It doesn't change much. It has a very strong carrier. So we've been using that throughout the mission to produce our 2-line elements that I've been sharing with you folks. And meanwhile, on the 2241 megahertz channel, we have 8 kilobit per second telemetry that we're presently in lock with and decoding. And we showed you that earlier, and we can certainly give you another view of what that stuff looks like. So we'll wipe out the bit container. We had about half a megabyte of data before when we last looked, and now we're over a megabyte of 8 kilobit per second data. And here's the telemetry that we've received so far. So we're getting some good data now, and getting a fairly good quantity of it for maybe later analysis. So that's the present status as we head towards translunar injection. The spacecraft is now less than 20,000 kilometers altitude, and we're a little over an hour and 10 minutes from the perigee. As I mentioned earlier, the exact timing of the translunar injection burn is not known by me, but will occur around perigee, and it will likely last many minutes. Perhaps somebody here watching the live stream has some more information that has been released. I haven't been searching the web because I've been busy with this, but typically a burn such as this translunar injection would occur over a few minutes around perigee, and where exactly it occurs really depends on the precise trajectory that the mission planners are trying to achieve. Yeah, just checking the status of ISRO official social media and website accounts. I haven't seen any updated data or information about the length of the translunar injection burn that Chandrayaan-3 will perform in the next approximately hour. So not sure whether we'll observe anything because the spacecraft will be descending rapidly. Also, the spacecraft's antenna orientation will likely not be in a favorable orientation for me to capture strong signals at that point. But all of that is entirely normal, and basically the spacecraft will go into kind of an autonomous mode, orientate itself, and fire its engine for however long it takes, and then once it emerges on the other side of the burn, it will reorientate for communications with the Earth. And following the trajectory, I would imagine it will come into range of the Indian Tracking Station 32-meter dish, probably about half an hour after the translunar injection burn, and be able to provide telemetry and ranging data to the ISRO ground station and provide them with any information about how the burn went. Yeah, somebody's asked, is that the sound of radio? Yes, that is the sound of Chandrayaan-3. That's its central carrier that I'm using to perform Doppler analysis, and that is what you are hearing. I'm going to change the pitch of it so it's not so high frequency at the moment. So that is live radio signals from Chandrayaan-3. And if you like, I will grab a hold of this and you can listen to some of the telemetry. That white noise you're hearing right now is the telemetry signal right here. I can open up the bandwidth a bit. And that's the telemetry signal. And we'll go back to our monitoring of the carrier. The shift in frequency of the carrier is caused by the Doppler effect, and that is what we are using to produce precise tracking data. Now, somebody's asked for an explanation of what we're seeing on the monitor right now. What we're seeing here on the screen right now is a waterfall plot. This is time. The vertical axis is time. So the top of the waterfall is now, and this is a few minutes ago. So you can see that the frames is 25 frames per second, so like a video frame rate. So it's a fairly fast waterfall. This is the central carrier of the Chandrayaan-3 signal that we're monitoring, this big spike here in the middle. And these are the data sidebands. This actually contains the spacecraft telemetry. And these are just artifacts of the mixing of all these signals together. On this particular channel, it sends relatively low rate data at 2 kilobits per second. On the one of the other channels that I just brought up here, same idea with the waterfall, just a different piece of software. This channel is sending 8 kilobit per second data, and right now we're actually decoding that data and writing it to the hard drive. So if you wanted to view that data, we could open the file. You can see we have a little over a megabyte of data downloaded so far. And this is live telemetry from Chandrayaan-3. It's binary data, primarily about probably spacecraft systems and all the different parameters that the ground controllers would be monitoring. And as I spoke of earlier, presently Chandrayaan-3 is in lock with the Deep Space Network, Deep Space Station 26, located in California at Goldstone. You can see here from the DSN Now website, the spacecraft is approximately 18,000 kilometers distant, approximately 17,000 kilometers in altitude above its Earth's subpoint, in other words, that point of the Earth immediately below the spacecraft. And it is rapidly descending towards perigee. At perigee, using the Hoffman transfer scheme, is the most optimal time to change the apogee of your orbit. So that is where the spacecraft will fire its main thruster or engine to propel it towards the moon for translunar injection. The precise timing of it hasn't been released by ISRO, nor has the length of the burn, but we can surmise that it will be around perigee, and I would assume it would last for a few minutes to gain sufficient acceleration to perform a successful translunar injection. Okay, somebody had asked me what we would see during the burn. Unfortunately, the spacecraft will probably have set at my location by the time the burn occurs, so we probably won't see anything occurring here, but if we could see it, we would see the pitch of the radio signal change and deviate away from the predicted pattern that the signal would follow. So if we look at, I don't know whether I've got a plot here, we've got the Doppler plot. So this highlighted area is approximately where the perigee of the orbit would occur. The predicted curve is the red and the gray line, and the Doppler data would deviate from that and begin its new trajectory towards the moon, at which point I would need to track that data over a period of time to develop a new trajectory model so we could track the spacecraft accurately. So that's what we would expect to see, and what we will see after the spacecraft comes back into view some hours later after the translunar injection. The Doppler curve will be different, and I will use that new Doppler curve to start to develop a new trajectory model and verify any ISRO claims about the orbit of the spacecraft. Now, somebody's asked if it's going to attain escape velocity. I don't think so. It won't necessarily need to escape the Earth's gravity. What it needs to is attain an orbit that it can reach the moon. And once it gets into the lunar hill sphere, or lunar gravitational influence, the Chandrayaan-3 spacecraft stack will be literally sucked into the moon and enter an orbit there, where it'll fire and do a lunar orbit insertion burn and enter a elliptical orbit of the moon using relatively little energy. So that's the goal. It's not necessary. It's not trying to escape the Earth-Moon system. It's just trying to propel it to get it within the range of the moon. So it's basically, it's like timing a shot to get the spacecraft to within the gravitational influence of the moon, so the moon's gravity can grab a hold of it. And then the spacecraft can use a very small amount of rocket power to enter a stable elliptical lunar orbit, at which point Chandrayaan-3 will engage in a number of similar maneuvers to how it raised its orbit around the Earth, but will in reverse around the moon. It will descend by steps towards a 100 kilometer by 100 kilometer orbit around the moon, where it will prepare to release the lander and then begin that phase of the mission. So as you can see, we're getting very strong signal levels now. I'm going to stop the 8 kilobit per second recording here, and I'm going to try a couple of the other channels that I haven't recorded a lot of data from over the last while, and see whether we can get some good telemetry data from them for posterity and later study. So let's have a look here. And there we go. I hadn't copied this guy yet, and we're getting good CRC lock. So we're going to run this for a while. This is a channel that is not normally on over North America. So we're getting some new data here, and we'll go have a look at that. Okay, so let's open that file up. It'll be a new file that we just started on that frequency. We've got a few kilobytes in there. Let's see if there's anything interesting here. We'll take a look at the ASCII, see if there's any plain text in here. I don't see anything overly interesting. Just binary data. Okay, so we'll let that run for a while. That's a new telemetry channel we haven't decoded before. So we will let that run and gather some data over the course of the next few minutes for later study. Somebody asks, is the sound in the background, is that CY3? Yes, it is. Yes, that's the central carrier of the spacecraft, and you're hearing its frequency change due to the Doppler effect. So its motion in space and our motion of rotating here on the Earth are creating that change in frequency. You can see the signal over the last, if you scroll back in this live stream, you'll notice that the signal has increased extraordinarily since we started the broadcast a few hours ago. And the spacecraft is now presently a little less than 15,000 kilometers in altitude and approximately 16,000 kilometers distant from my ground station. So the perigee of the orbit is about 55 minutes from now. So the next hour is going to be rather dynamic tracking-wise. Depending on how accurate the orbital elements are, I may have to do some manual adjustments in aiming. So far everything is bang on track. And we're looking at good Doppler data being recorded. And I'm just changing the frequency offset to lower the pitch of the tone for now. And we'll go check on our telemetry gathering, and everything seems to be going well there. Let's have an updated view. So we've got about 100 kilobits of data now. Have a quick look at this. You can see repeating patterns. That's to be expected. So that's probably just, once you dissect how the frames are structured, and there'll be subframes, and there'll be all kinds of stuff in here related to the status of the spacecraft and any other experiments and things that they may have on board. So there seems to be a reoccurring ADC ASCII characters there. You can see a bit here, more interesting stuff. If you look at the bit raster, you can see counters. These will be frame counters and maybe a clock on board the spacecraft. and then you can see the bit structure. Here's a byte kind of view of the data, so you can get to see some of the structure of it. We'll use this data later for some study of the data structures that the space mission used, more for just self-education and interest. This will probably be the last time I'm able to decode signals from the spacecraft during this perigee pass, because this will be the last time it's this close to the Earth. So hopefully in less than an hour it will be propelled out towards the moon, and that's where Chandrayaan-3 will exist for the far-term future, hopefully. Somebody asked if I'll be live for the lunar insertion burn. As I've said before, I will likely not be able to see the burn because the perigee is very low and over the Atlantic Ocean just north of Brazil at approximately 230 kilometers altitude. So I will probably have lost a signal before then, or I definitely will have lost a signal. The only thing we don't know is how long the translunar injection burn is and where exactly around perigee it will occur. So there's a bit of uncertainty there, but I highly doubt that I will observe the translunar injection directly. So that tone you're hearing in the background is the carrier signal from Chandrayaan-3 that we're using for doppler study of the trajectory of the spacecraft. Chandrayaan-3 is a little less than an hour from perigee and rapidly approaching the Earth, where it is expected to perform its translunar injection burn. Right now, the spacecraft is a little over 13,000 kilometers in range, approximately 15,000 kilometers distance from my ground station, and rapidly approaching perigee. The orbit is highly elliptical, and at this stage of the orbit, the spacecraft's relative motion through the sky will rapidly increase. The Russians call this type of orbit Molina, which translates into lightning, which describes this phase of the orbit very well. So somebody's asked about the delta V and the duration of the burn. I don't know. We don't know precisely. ISRO has not released any data like that. So we'd just be guessing. We don't know the duration of the burn. And I'm not sure whether we have precise masses for the spacecraft, and particularly what remaining fuel would be on board right now. So it'll be interesting to see. Somebody just posted it'll probably be a 20-minute burn. So there is a possibility that I might just see the beginning of that before the spacecraft sets here. Well, we won't know until we observe. And as I mentioned earlier, I'm not sure whether the radio signals will hold out due to local attenuation near my horizon from trees and other objects, and also due to the spacecraft's antenna orientation. As it approaches perigee, the antenna does no longer hold its direction towards the Earth, and also the beam of the antenna is probably fairly narrow, so at that low altitude there's a good chance that I won't be able to copy a reliable signal from the spacecraft. Okay, so we're getting a good amount of telemetry data from the 2268 channel, which I hadn't observed too much of before because it's usually off over North America. So fortunately during this run-up to the translunar injection it's active, so I'm able to get some data. I've got some data from the other channels, and before things get too far along here, I'll stop this and we'll go up to the 284 and get an updated sample of data there. So we've got a representational sample of all of the different channels before the translunar injection. Let's see what happens here. There we go. We're getting good data finally from the 2284.6 channel. So we'll collect some stuff there. This is lower rate data. This is 2 kilobit per second telemetry. Let's go have a look at that. Won't be much there yet, but we'll have a quick look at the structure of the data. Let's see what's going on here. Don't see any recorded data there yet. Maybe I've got something set wrong. It should be writing. Unless it's not sending anything other than the sync. Let's start that one again. Let's see what happens. Oh, I guess it just wasn't enough data to write the buffer. All seems fine. Let's have a look at what we got there. Okay, so a little bit of telemetry from that channel, so everything seems fine. So we'll just keep monitoring that for a few minutes and get a few minutes of data there. As you can see, the signal levels have greatly increased. They were much lower when we first started, around 3 or 4 dB. Now it's about 10 dB louder as the spacecraft approaches about 12,000 kilometers in altitude, and range is approximately 13,000 kilometers at the moment. So the perigee is in approximately 40 minutes, a little bit more than that. So that's where the translunar injection burn will occur around. One of the viewers here is advised that it's probably going to be about a 20-minute burn, similar to Chandrayaan-3. So we'll see if we observe anything. If they start the burn a bit earlier, there's a chance I might observe something if the radio signal holds out. But I'm not counting on it. So the normal process for studying a burn like this, if we don't observe it, is you observe the spacecraft prior to the burn that it's going to perform, and then when it sets, it performs the burn. You don't see it, and then hours later the spacecraft will rise above your horizon again, and then you measure Doppler from it and note the difference. And then from that you can start to develop a new trajectory, and once you have enough data, you will be able to predict the new orbit and determine whether the burn was successful or not. And that's largely the process space agencies like the ISRO will use. It's highly unlikely the spacecraft will be tracked by a ground station while the TLI burn is performed. It'll probably be automated by the spacecraft itself, and once the spacecraft rises shortly after the burn over India, the ground controllers will lock onto it, likely with their 32-meter dish, and start ranging with the spacecraft to determine its range and measure its trajectory and determine how successful the burn was. That's the typical process, and I use a very similar process here for monitoring such activities if you don't actually see the actual burn itself, which is quite a rare thing. Most major burns like this occur at perigees, and oftentimes those perigees can be very awkward places around the Earth. So not even the launching nation may have the ability to view it. So okay, so far we're getting really good signals from the spacecraft. We're now at about 10,000 kilometers altitude, 12,000 kilometers downrange distance. The tracking system here is having no problem maintaining excellent signal levels with Chandrayaan-3 as it rapidly approaches perigee and the translunar injection burn. We're still gathering telemetry from the spacecraft. I've noticed the signal levels have started to drop a bit, which could be indicative of the orientation of the spacecraft is starting to change, and the antenna is not quite perfectly pointed in my direction anymore. As the spacecraft's altitude lowers, the beam pattern of the antenna will become more selective as to the part of the Earth that it's looking at, and we may see fading as different parts of the beam pattern pass over the ground station here, and that could determine how well we hear into the perigee area of the trajectory. So far so good. Signal levels look good. We'll keep an eye on that. What you will see in particularly this plot is fading. We call on the amateur radio speak QSB. The fading will start to occur over minutes, with the signal rising and falling as we start to view different viewpoints of the spacecraft antenna. This is entirely normal and not indicative of any problems with the spacecraft. Yeah, someone asked about the lunar orbit insertion burn. So basically what will happen is Chandrayaan-3 is targeting the moon with this translunar injection burn. This burn will get Chandrayaan-3's stack into the lunar hill sphere, and once it arrives in the vicinity of the moon, Chandrayaan-3 will again perform a lunar orbit insertion burn to enter into a highly elliptical orbit of the moon, which is the lowest energy way of entering a lunar orbit, and then successively fire its engine to lower its apogees around the moon in a sequence of maneuvers very similar to the orbit raising burns around the Earth. If you look at the plot the ISRO has shared for both this mission and Chandrayaan-3, you'll see a very similar pattern. The Chinese have also used similar insertion methods, and so have the US and Russian probes over the years. So the upcoming burn, actually, strictly speaking, will still leave the spacecraft in an Earth orbit, except the orbit is very, very highly elliptical, with an apogee that is out beyond the moon. The timing of this translunar injection burn will allow that orbit to essentially cross paths with the moon and put the Chandrayaan-3 spacecraft stack into the lunar hill sphere, or into the gravitational influence of the moon. So once it's within the gravitational influence, at the correct time, it will perform a translunar, or a lunar orbit insertion burn with a small amount of energy, and place it in a highly elliptical orbit of the moon at that point. So it's a little bit of a ballet in gravity. So right now we're targeting the moon itself. This burn will place Chandrayaan-3 on a trajectory to literally encounter the moon very closely, well within the lunar's gravitational influence, where a second burn, the lunar orbit insertion burn, will occur to place the spacecraft stack into a precise elliptical orbit around the moon, where then it will begin another sequence of orbital maneuvers to lower the apogee until it's in a 100 kilometer by 100 kilometer circular orbit of the moon, where it will begin operations to release the lander and proceed with that phase of the mission. We're now starting to see fading on the signal, as expected. So we're starting to see really strong peaks in signal and then fades over the course of minutes. Right now you can see the really strong signals that we're receiving from the telemetry signal on this channel. Just ginormous. I'm going to turn on the recorder briefly just to get a sample of this. This is our chance to gather some high quality telemetry data for later study. I'll keep these samples short. For most of the study that we want to do is just looking at the frame structure, etc. So I'll keep them under 100 megabyte IQ recordings so they can be easily shared with other researchers later. Okay, that's good. And we'll stop the recording here. We'll go back to 68 and 2, and we'll do another 8 kilobit per second recording, and we got lock on that signal, no problem. We'll take another 100 megabytes of this guy. So right now we're just going to do a quick data gather as the spacecraft passes 9,000 kilometers altitude, downrange distance of 10,000 kilometers from my ground station. And we still have good tracking. The two-line element that I'm using is providing good dish pointing information, even as the spacecraft is approaching perigee now. We're approximately 30 minutes from perigee, where the translunar injection burn will occur. Now we're going to change frequency to with the next channel, and we're going to quickly gather some more data. So we have IQ recordings of the data. I'm also doing an IQ recording of the 2203.2 megahertz channel. You can hear the pitch of the signal is starting to change. It's slowing down. So we're approaching Doppler reversal, which is a significant milestone in the Doppler analysis side of things. In a few seconds I'll end this recording here, and then we'll go back into Doppler mode. And you can see here on this channel those changing tones. That's DSS 26 from the Deep Space Network ranging the Chandrayaan stack. They're actually engaged in measuring the distance to the spacecraft for precise orbital analysis. So we're going to leave it on this channel to continue to decode further telemetry, and we will switch back over here. Okay, I'm going to set this up here so you can start to monitor the pitch, and notice that the carrier is now starting to descend in pitch. So we will bring up the Doppler software and get an update on that, which will take a few minutes to process. Before we do that, let's have a quick look at where in the orbit Chandrayaan-3 is. So we're going to update here, and we'll wobble over here, and you can see the location of Chandrayaan-3 with respect to the perigee, this little dot over here. So we're starting to rapidly approach it. I see there's a lot of comments occurring here right now. Just let me focus on getting the Doppler data up so I can show you guys that. I'm going to do the fast Fourier transform. So this will take a couple of minutes. Move that off the screen, put the trajectory over here so you guys can continue to monitor the pitch of the signal. As I noted earlier, the Doppler frequency will change direction. It's the Doppler reversal, the knee of the curve. We're now descending. The Doppler signal from the spacecraft is now behaving like a low Earth orbit satellite. It is very close to the Earth now. Altitude is presently 7,500 kilometers, downrange distance approximately 9,000 kilometers. So the spacecraft is rapidly approaching the Earth and perigee. So as we update the 3D plot, you can see the circle here that I'm highlighting. That's the footprint of the radio signal of the satellite. This is where I'm located, where the cross is right now. So we're still in a good spot to see the spacecraft. I'm approximately 42 degrees elevation and pointing a little bit west of south. So things are all proceeding normally. We've got really good track, really good signal. The two-line element that we've created over the last 5 to 6 days during its last orbit is very accurate. So we're getting really good signal tracking. I'm just going to change the frequency here. So then in a couple of minutes I will be able to bring up the present status of the Doppler signal. You can see for yourself where on the curve it is and relate that to the signal levels. So one thing I'm going to do is I'm going to change the tracking interval, because now that we're approaching perigee, we will want to increase that so the antenna will stay accurately pointed at the spacecraft. Presently it's updating every minute or so, and I'm going to change that to every 20 seconds. Okay, so that should keep us fairly accurate. You could see that, just even me stopping the tracking there for a few seconds while I change the tracking interval caused the signal to drop down a bit. Now we're back on track. So every 20 seconds the tracking software will send an update to the rotors and keep the antenna aimed precisely at Chandrayaan-3. Okay, so now, meanwhile, back on our Doppler curve, RF plot. We got that already here. So now we'll do our plot, and we can see the progress of Chandrayaan-3 towards perigee and the translunar injection burn. We're getting a bit of a fade here, and this is quite common. This is what I was referring to earlier. You'll see it fade down and fade up. What I suspect is going on here is the orientation of the antenna is no longer favoring me or this part of the Earth, and we are passing through a null, probably in one of its side lobes, and now the signal is picking back up again, and we're probably looking into a peak in one of the side lobes. Okay, that's not quite long enough. So you can see the signal intensity is rapidly increasing here. So, and the Doppler rate is getting to a point where I need to keep up on it. So this is the part of tracking something like this that can get a little, where it gets a little bit more interesting than what we've been observing over the last few hours. As the spacecraft approaches perigee or is in low Earth orbit, the attention required by the operator is much, much greater to collect data and conduct operations. Okay, we're still getting good 8 kilobit per second on the primary, I believe the primary channel that the Deep Space Network is using. Here you can see the Doppler plot. You can see we're well past the, and very interestingly, it appears that there is a significant change in trajectory that has occurred already. Now, I'm not sure whether this is error in my model or whether this is indicative of some kind of activity from the spacecraft. I'll chalk it up to error at the moment, and we will conduct a bit more analysis. When you're monitoring so close to a perigee, small amounts of error in your orbital model can be very significant. Okay, so what we want is we want to gather all of that data. Okay, and now we're going to quit there. And we are going to clean it up and then do a quick analysis of it. We won't have enough time probably to update the orbital elements, because things are happening pretty rapidly right now. And if I need to, I will take manual control of the rotors and keep the signal levels as high as possible. So here we got the, Okay, so now we're going to quit out of that, and we're going to reload test C, and then do an orbital correction. Okay. No, everything seems to be fine. I guess the maybe the TLE that I have loaded in there is an earlier version. So everything seems fine without having to change any of the orbital parameters, so nothing has occurred. There was a small error on probably my part in the data that I used in the plot overlay. So we can see we're now well into the part of the Doppler curve where the signal is now going to rapidly descend in pitch. Even though right now you're probably hearing it go up, that's just due to a sideband issue because I haven't adjusted the frequency here yet. So that's more like it. I'm going to slow down this plot to allow you guys to see what happens over the next 10 minutes or so. So the plot is now set to record to 10-minute intervals. So this screen here will last for 10 minutes. Sorry I'm unable to keep up to the chatting going on here, like needing to keep an eye on the instruments and the antennas, and I may have to rapidly intervene on tracking manually. So I'm just keeping an eye on all this kind of stuff. Because if we are going to see anything from the translunar injection, it could very well start in 10 minutes if it has a 20-minute burn duration, which potentially could put it within view, and we'd hate to miss that if we get to see a glimpse of the translunar injection here. So let's update our plot. You can see the rapid change in the position of Chandrayaan-3, and let's rotate our plot towards the perigee, which is this little dot right here. As the Earth rotates into position and Chandrayaan-3 moves along its trajectory, it'll be approximately there is where the perigee will occur. And as you can see from the slowed down plot, and the reason why the frequency changes like it does is it passes through the, and you hear the other sideband. I could change this over to perhaps USB, and it'll be less of an issue. And I'll just set it up as a higher pitch so we don't have to change that much. Okay, so here we are plunging towards perigee. We're now past, we're about 4,500 kilometers altitude, downrange distance of approximately 6,200 kilometers. Everything seems fine with Chandrayaan-3. No obvious issues with radio signals or nothing observed that hasn't been seen before in previous perigees. So you can see the rapid change in frequency is occurring. Here's the most recent Doppler update plot from a few minutes ago. You can see the trajectory from my point of view of the spacecraft is starting to rapidly head towards the horizon. Here is the present position of Chandrayaan-3, and this circle here is the footprint that we would expect to receive radio signals. My location is approximately here, so when that circle is no longer overlapping me, I will no longer be able to hear Chandrayaan-3. This little dot here is where perigee will occur in its orbit. The Earth is rotating underneath the orbit, so that position will be approximately here once Chandrayaan-3 arrives. You'll see that. I'll keep the live stream going until we pass through perigee, even though I may lose signal, so we can discuss that. And a few hours, many hours after the translunar injection, I would expect to get acquisition of signal again as the spacecraft heads out towards the moon and be able to confirm its trajectory. You're seeing here the fading of the signal that I reported earlier has begun. The system here is now tracking at 20-second intervals. The tracking data is looking a little bit out, which is not unexpected. The antenna is a fairly narrow beam, and the spacecraft is rapidly moving through the sky at this point. If you could visually see it, it would be physically moving. So, it would be moving from moment to moment. It was something you could detect easily by eye if you were looking at it with a pair of binoculars, say. And it would probably be visible in a pair of binoculars if it was nighttime. So we've just passed 4,000 kilometers altitude, downrange distance of 58,000 kilometers. Everything's looking normal. Nothing you're seeing here is indicative of any issues with the spacecraft. This is just what it does when it's hurtling towards perigee. We still have lock on the signal on the 8 kilobit per second channel, as you can see here. So we're still collecting telemetry. Just going to check the status of the deep space network and see whether it's probably to the point. Yep, they're still in lock. DSS 26 is still tracking Chandrayaan-3, and they are in lock. I would expect the deep space station to probably discontinue tracking shortly, as the spacecraft's angular position will start to rapidly change in the sky, and that big old dish is not going to be able to keep up with it. Again, I apologize, I'm not responding to the chat at the moment, just trying to keep my eyes on the ball here to keep things adjusted for you folks. I will, of course, respond once I have lost the signal. I will be happy to respond to any questions that pop up in the thread. If any other viewers or see and know the answers for people, that'd be greatly appreciated at this stage. So what we're seeing right now is the radio signal from Chandrayaan-3. It's rapidly changing in frequency. It has passed the doppler reversal. It's descending rapidly towards perigee, and in this case it will fire its engine and begin the translunar injection burn in mere minutes. It could be as early as half past the hour locally here. So we could see the translunar injection burn begin as shortly, or they could be delaying it until after centering it not quite perfectly on perigee. I'm not quite sure what their mission plan is. The ISRO has not released specific data on when and how long the translunar injection burn will occur. If it does occur at all while we're observing radio signals, we would see a deviation from the Doppler curve that we're seeing now. It might not be extremely obvious to us, depending on our orientation and how the spacecraft velocity relative to my ground station changes. It might be rather subtle if we do see anything at all. So somebody asked if we could reverse engineer what the Deep Space Network is providing. Back in the day, yes. The NASA DSN Now website has kind of reduced the resolution of their data recently due to security concerns, and which has produced less than accurate data from them. So it's not so much useful anymore for tracking purposes. It's certainly helpful for just keeping track generally of the missions, which is its real intent, but not for generating orbital elements. Okay, we're seeing our first big fade. This is entirely normal, nothing unusual about this. What's occurring right now as the spacecraft passes 2,700 kilometers altitude, downrange distance of 5,400 kilometers, is we're not seeing the antenna orientated towards my ground station anymore. So we are seeing the spacecraft from an odd angle. So its antenna is likely not aimed at us. The other possibility is the spacecraft is preparing for the translunar injection and has reorientated itself to prepare to fire its engine. And most likely it will be a prograde burn along the axis of the trajectory. So the antenna is probably no longer aimed at us. So we could have witnessed the spacecraft engaging in some sort of attitude change to prepare for the translunar injection, which I would expect to occur within minutes. According to the DSN Now website, the spacecraft is still in lock with DSS-26, and I would assume within moments the spacecraft will likely unlock from the deep space station to prepare for its translunar injection burn. We still have a very weak signal from Chandrayaan-3 here, and we're about to lose signal. And we're going to do an update on the plot. As you can see, my elevation to the spacecraft is 4 degrees at the moment, and we are about to lose signal. So everything up to this point is entirely normal. Most likely that loss of signal there was occurred due to a normal loss of signal moment, attenuation from trees and other objects in my vicinity, and the spacecraft is setting. Now I will continue to report on the location of the spacecraft. As you can see, DSN Now has updated, and Chandrayaan-3 is no longer in lock or in communication with the Deep Space Network, DSS-26. This is entirely normal. The spacecraft is now moving at a very rapid rate through the sky, and also approaching a low elevation for the Deep Space Network dish. The dish itself is rather large and cannot move physically fast enough to keep track of such a low object, and also maintaining communication lock and transmitting high power signal at a low elevation is not something that deep space antennas normally do. So this is entirely normal that they would have discontinued communication. If Chandrayaan-3 is communicating with anything now, it may very well be using an ESA site, and I'm not sure. Let's see if we can get some information about if any of the ES track sites are engaged. And Karuna, which would theoretically be in range for, yes, they have, just checking now, there will be TLI coverage from the ESA station. So they're going to start tracking in 1 minute and 26 seconds. Unfortunately, the ESA station, ESA website doesn't provide a lot of details about what's going on, but at least we know that the station will be tracking. So we'll keep an eye on that for updates. As you can see here, we have lost signal from Chandrayaan-3, which is entirely normal. The spacecraft is set from my ground station location. We're watching the trajectory, which will be still golden for the translunar injection burn. If it is centered around perigee, and one of our viewers had noted earlier that it would be an approximately 20-minute burn if similar to Chandrayaan-2, it should be burning now. So we shall see. The ESA ground station is approximately 30 seconds from acquisition of signal, and it will have an 8-minute approximately 9-minute view of the spacecraft as it passes through perigee and conducts the translunar injection. So the spacecraft is moving at quite a rate right now. Altitude is approximately 1,400 kilometers. Downrange distance from my ground station is 5,900 kilometers and increasing, obviously. So we'll just keep a track of the altitude. So the altitude is rapidly decreasing. Now the velocity, relative velocity of the spacecraft is very high right now. We're now passing through 1,300 kilometers altitude. The ESA ground station is started tracking, as indicated that it has lock with the Chandrayaan-3 mission. I'll bring that up. So things are looking good there. These signals indicate, and this bar indicates that they've have communication with Chandrayaan-3. The ground station is located approximately here. You can see it here on the map. Updating the position of Chandrayaan-3. The little dot right here is perigee, and that should be approximately the center of the prolonged translunar injection burn. We should, in theory, be in the burn now if it is centered on the perigee. We don't know when the translunar injection burn will exactly start. Is it delayed somewhat or not? We didn't see evidence of it in the doppler coming into the perigee before I had loss of signal. So I'm assuming that it was beginning at approximately 10 minutes from perigee. Perigee is at approximately 1841 UTC, and we are now at approximately 1836. So if the translunar injection is centered on perigee, it should be engaged. It should be occurring right now. ESA ground station has been in lock for the last 2 minutes 12 seconds. And it's expected to remain tracking Chandrayaan-3 for the next 6 minutes or so. So we'll keep an eye on that. Everything seems to be normal. Now, the translunar injection burn is not an instantaneous thing. They require time to get the right amount of acceleration to get the Chandrayaan-3 stack to the moon. So from my understanding, that burn will last about 20 minutes. It should be centered around perigee. They may either go a little bit earlier or later than that, depending on any kind of other orbital astrodynamic trick that they might be up to just give the spacecraft stack just the right trajectory to go where they need it to go to encounter the moon. But nominally speaking, we're expecting translunar injection to be centered on perigee, which is this little dot right here where my cross is. Chandrayaan-3 is now in communication with the ESA ground station in northern South America. And we continue to monitor Okay, as you can see, I'm just going to shut off my recorders here. And then we'll go back to monitoring what we can from ESA. So we have another 4 minutes. The spacecraft altitude is now below 1,000 kilometers. We're now passing through perigee, probably within the error of the trajectory model that we have. Perigee is occurring as we speak. So one may wonder, is this a big scary moment in the mission? I would say no. ISRO has engaged a number of perigee burns throughout the mission so far. I would imagine this burn will be routine and normal. As I noted earlier, this is the location of perigee from our present orbital model. Chandrayaan-3 is located here. It is, for all intents and purposes, at perigee, and most likely its engines are firing right now, performing the translunar injection burn. So the ESA ground station reports that it will lose signal in approximately 3 minutes. It has been tracking Chandrayaan-3 for a little under 6 minutes. So this gives you a good idea of what satellite tracking is all about. Oftentimes you don't get to see the event that you're all interested in. You need to collect enough data before and after the event so you can gain enough knowledge as to how well the event occurred. And that's what we'll be doing here. In a few hours, Chandrayaan-3, whether the burn was successful or not, will rise back towards apogee and will pass over my ground station, and at which point I will collect further Doppler data and be able to compare it to the current orbital model prior to translunar injection and see what kind of difference there is and determine whether the translunar injection was successful or not. ESA and ISRO are collecting data presently, and they'll know much sooner than me. As you can see from the ground plot here, you'll see that the trajectory roughly passes over southern Africa, and the spacecraft will then go into view of India, and the big 32-meter dish located there will presumably take up communication with Chandrayaan-3 shortly after the translunar injection burn and be able to conduct ranging and other more sophisticated orbital analysis work and update the orbit. And at which point I would expect some sort of statement from ISRO after they've been able to study the results of the burn and their telemetry and the trajectory that they measure, and be able to provide feedback on how things went. As you can see, we're rapidly approaching perigee. Presently the spacecraft is probably less than 300 kilometers over the Earth, and just burning by. I will see Chandrayaan-3 most likely this night as the spacecraft heads back up in altitude and becomes more stellar-like, and the Earth's rotation brings it back into my view. At which point I will collect Doppler data from it for the entire paths, and we'll compare that and conduct a Doppler analysis. So tracking has ended with the ESA ground station site. I would anticipate the next ground station to acquire the spacecraft to be in India, unless of course there is some kind of agreement with a station in Africa that I'm not aware of. So we'll take down the ESA track, and as you can see, we are now at perigee. This theoretically should be the center of the translunar injection burn. However, there are reasons why the burn may be centered not precisely on the perigee, so I'm not 100% sure when the burn began or when it'll end. We have some rough information shared by some viewers that the Chandrayaan-2 burn was approximately 20 minutes. So with that, we will continue to monitor for a few more minutes, and I'll have a look at your questions and see if there's anything here I can help with. Somebody asked if the ESA ground station is no longer tracking. One must understand that these spacecraft are automated. They have enough brains and computer power on board to conduct these kind of operations completely autonomously. No one needs to monitor the spacecraft. It will store any data that it needs to store to be shared with the ground station later. So there's nothing abnormal about this. It's quite normal that burns of this type may not be in view of a ground station. And as I said, the next big event in the mission will be acquisition of signal, most likely by the large 32-meter dish in India, where they will conduct ranging and communication activities with the spacecraft stack to determine the status of the trajectory and determine how well the spacecraft performed during the translunar injection burn. Here, somebody reported 1203 second burn duration. Sounds about right. So more than likely the burn is ongoing as we speak. Here you can see that Chandrayaan-3 should be ascending away from the Earth now. This will be the last time Chandrayaan-3 will be this close to Earth if the translunar injection burn is successful. And we're saying goodbye. She's off to the moon. Somebody asked if I'll be able to get data from their antenna. Highly unlikely, unless the ISRO shares that publicly, which I don't think they will. So we have to collect it from our own antennas. We might get some data from Europe. I don't know if anybody's recording Doppler data there. That could help me perform an analysis before the spacecraft rises over me. Either way, I'll know within the next 12 to 24 hours how the burn went and what present trajectory Chandrayaan-3 is headed out on. My confidence level in this burn are very high. The spacecraft has performed a number of burns to this point in the mission so far, almost the exact same type of profile. I think about the only difference on this burn is it might be a bit longer. So, not 100% sure, but they have lots of practice, and the spacecraft has demonstrated the ability to do this over and over and over again. So I believe it is just fine. The real tricky moment, as been on the previous mission, will be the landing phase on the moon. ISRO is very, very adept at these kind of maneuvers. So without having any data, I would confidently say that they've probably nailed the translunar injection and things will be fine. Of course, we will continue to monitor and measure and confirm any statements that the ISRO releases publicly. Yes, not knowing what's going to happen can be stressful, but again, I think we have a reliable source of information based on past performance. This is not a risky phase in the mission based on previous experience. It's fairly routine behavior and activity that the ISRO has performed over and over again on this and other missions, and all with 100% success rate. So I don't think this is a highly risky moment in the mission. It's just something we got a unique view of. Okay, so you can see Chandrayaan-3 is, I'm using the old trajectory data here now, which is not going to be greatly different then if the translunar injection had gone off on schedule, the divergence in the trajectory will occur more and more and more as time goes on. So for the next little while, this trajectory will be fine to give us a rough indication of where Chandrayaan-3 is with respect to ground stations. And I would expect in the next 20 to 30 minutes that Chandrayaan-3 will be in range of India and be able to start to collect data so they can carry out with ranging and trajectory analysis, and maybe they'll provide a statement after they have time to collect enough data. But it does take some time. They'll be able to probably know right away from the telemetry data as to how the spacecraft performed. In other words, the duration of the burn, how much fuel is remaining, all that kind of stuff. What they won't have immediately is the actual results of the trajectory, because they'll need to track it a little bit, collect some data before they can say 100%, but they have far more sophisticated means than me, so they'll be able to put that together fairly soon, and I would assume that they would be able to provide some kind of public statement today as to the progress of the TLI. As you can see, the spacecraft is now rapidly departing the Earth. The footprint of the spacecraft over the Earth is going to rapidly increase over the next few minutes. Somebody asked how long it usually takes. Depends on what methods you have at your disposal. For me, it would take a bit of an X pass to be able to compare the data to see how it has evolved and then fit up a new orbit. For a space agency, it would probably be fairly quickly, depending on the trajectory data that they collect and they have on board the spacecraft. I would imagine the spacecraft itself has rather rudimentary navigation systems on it, so it'll be likely mostly ranging from the ground station and positional data. The spacecraft will be rising over India during darkness, so it is possible that they could be optically tracking it as well, which would provide really accurate data quite quickly to them. We shall see. We'll see what they have to say once they get some data. Somebody asked when I can give my next update. Probably within the next 24 hours. I'll need to reacquire signal, and that'll occur sometime in the next 12 hours, and then once I have enough time to gather data to perform a long enough arc of a curve to compare it to the previous orbit, and then we can start to figure out what's going on from there. So it's not instantaneous, but it is something that someone like me with limited equipment can do and study it. So some of the questions here about antennas and everything else, if you watch back in the video, I go through some details about that. There's also some links in the discussion. If you scroll back, you'll find answers to that. If you want to learn more about the hobby, Google is your friend. My Riddles in the Sky blog that I share with a few other satellite trackers has some frequently asked questions about it and links for you to look at. Have a look at the satellite tracking channel website. I do apologize, some of the videos are long and there's not a lot of commentary, but it gives you kind of some idea of some of the techniques we use. So with that, folks, I think I'm going to wrap up the live stream here in another couple minutes. We'll continue to track the footprint of Chandrayaan-3, and I think our next update will be something from ISRO. They will have telemetry once the spacecraft footprint covers India, where the big 32-meter dish is. Probably in the next hour they'll have telemetry from the spacecraft and to be able to find out some basic information about how the TLI went, and then they will be able to track the satellite and get trajectory information from it, range to it, etc., and then determine its current trajectory. So with that, folks, I think I will wrap things up, and thanks everybody for watching and for all your questions, and have a good night, because I'm sure there's a lot of sleepy people in India that need to get some sleep now. One last thing I'll do before I sign off is I'll do the final Doppler analysis for the descent into perigee here, and post that, and then I'll say good day.